BTEC Applied Science. This is a Unit 1 physics paper. Another one I'm doing. This is from a sample assessment, basically for teachers or, before the course started. But it's a proper physics paper. Let's have a go at it. So, again, write neatly with a black pen, bring a ruler. Bring your own calculator, the one that you bring to every lesson, the one that you know where all the buttons are. You're not going to waste time figuring out how to do things like square roots or whatever. Always look at how many marks there are for a question. If you haven't got a clue, leave it and then come back to it later and write something down. Don't leave it blank. 30 minutes should be enough. But you need to get your skates on, okay? You don't have time to relax. If you know your stuff, 30 minutes should be more than enough time. This is the front of the paper. They used to have the 3 papers all together. Now they do them separately. In the physics, you get a formula sheet. And these are the formulas that you will need. We'll see in the paper, there's actually another one that you need, which you're not given. But anyway, so this is what's on the formula sheet. So let's crack on. Figure 1 shows a guitar. The strings on a guitar are different thicknesses. When the string on a guitar is plucked, a stationary wave is set up and the sound is produced. Figure 2 shows how a stationary wave on a stretch spring might be studied. So hopefully you've seen this experiment. You've got this vibration generator going yeah, and then the string's going up and down. The string there's a pulley and a mass hanging over the end of the pulley, and at certain frequencies you get these standing wave patterns. Okay, the diagram shows the first mode of vibration of the string. Label a node and an antinode. Well, we know that an antinode is where the string is moving lots and lots. That's maximum amplitude there. There's an antinode. And the node is where the string isn't moving at all. So you can either have there or there. Okay. You can have either there or there. A better answer would actually be that one. Okay, because it's nowhere near the vibration generator. Anyway, nodes at the ends, antinode in the middle. State the relationship between the distance PQ and the wavelength of the wave. Well, you should know that each loop is half a wavelength. So basically, the distance PQ is lambda over 2. It's half a wavelength. Okay, each loop is half a wavelength. And for your first harmonic, your fundamental, you know what I'm on about because you've revised, the length of the string is half a wavelength. Draw the second mode of vibration. So the second harmonic is 2 loops, not 1 loop, but 2 loops. So it's like this. So there you go. And that's the second harmonic. The third harmonic would be 3 loops, etc. Stationary waves are seen on the string only when the vibration generator is set to certain frequencies. Explain why stationary waves are only seen at certain frequencies. So I've done a bit of typing here. Basically, the length of the string has to be a whole number of half wavelengths. In other words, the length of the string can be 1 half wavelength, or it can be 2 half wavelengths, or it can be 3 half wavelengths, etc. But the length of the string has to be a whole number of half wavelengths. I've said they're called harmonics, and that only happens at certain frequencies. Okay, so for each harmonic, it only happens at a certain frequency. Okay, which are multiples of the fundamental, by the way. Bit of waffle at the start of this one. Oceanographers can understand the effects of coastal or water waves. Okay, blah, blah. 2 graphs, water waves. Now, hopefully, look at the graphs. Can you see the difference between them? hopefully you will see, because it's very important and you won't have a clue if you don't. This one is displacement against time, and this one is displacement against distance. So I talk a lot about this on my videos. There are two graphs, displacement time and displacement distance. Now on both of them, the amplitude is the maximum displacement, and that's the same on both of them. And looking at the graph, hopefully you'll see that the amplitude, now this is centimeters, so it's 1.6, isn't it? The amplitude is 1.6, and that's the same on this one as well. So the amplitude is the same. However, on the time one, the time for one oscillation is there, and the time is 1.5 seconds. Whereas on this one, this is distance. So the distance on this graph, okay, is a wavelength. And the wavelength there, well, that's 5, so it's one little square less than 5, so it's 4.8. So my wavelength, which is the distance between adjacent points which oscillate in phase, is 4.8 centimeters. Now, I'm just looking at the graph. I haven't even looked at the questions yet. Of course I have, but just imagine I'm just looking at the graphs and figuring what the hell they're about. Now let's have a go at the questions, and the questions say, so first of all, use the graphs to give the amplitude of the wave. Well, as I said, I've already done that. The amplitude is 1.6 centimeters. The mark scheme says plus or minus half a square. So if you said 1.55 to 1.65, you'd be okay. If you said 1.5, then no, you'd get it wrong. Give the wavelength of the wave, and the wavelength we said was 4.8 centimeters was the wavelength. Calculate the frequency of the wave. Now you might be thinking, oh, what am I going to do? Am I going to do F equals V over lambda? And no, because we don't know the velocity. The equation you should know is that the frequency is 1 over the period, isn't it? Yeah, and I said there was an equation that you'd need, which you weren't given. So the frequency is 1 over the period. So the frequency is 1 over 1.5, because that's the period of the wave. And on your calculator, 0.6666. But basically, if I do 2 sig figs, I'll do 0.67 hertz is the frequency. 0.67 hertz. Fiber optic cables are used in some broadband networks. Give one use of fiber optics in medicine. Well, endoscopy. Yeah, when you do like keyhole surgery and you get your endoscope and you look inside somebody's body, or you put it down the throat, or you put it in the other end and have a look in whatever. So endoscopy, yes, I think because you put it in somebody's end, whatever. Endoscopy will do. The use of fiber optic cables relies on total internal reflection. Explain why there is total internal reflection in an optical fiber. 3 marks. Explain total internal reflection. 3 marks. So I'll show you the answer that I've typed. Okay. When the angle of incidence, a light ray going towards a less dense medium, is greater than a certain critical angle, then refraction can't occur, so total internal reflection occurs. Now, let me explain that if you don't understand it. You know, this isn't for the paper, this is just for your understanding. So let's say we had glass and we had air. So that's glass, yeah, and that's air there. Now, if we have a ray of light, let's say this ray of light coming here. Now that ray of light, which is in the glass and it's trying to get out of the glass, okay, now what it might do is something like this, and it's refracting and it's bending away from the normal. When you go from more dense to less dense, you bend away from the normal. So there's that angle there, there's that angle there, and this second angle is bigger. Now, if this angle here is big enough, then what happens is, there's my ray of light. In fact, if it's bigger than something, we call it the critical angle. So if that angle there is bigger than a critical angle, then the ray of light can't bend more than 90 degrees. So instead of refracting, it will reflect, and all of it will reflect inside the glass. And that's total internal reflection. Total, because we always get a little bit of reflection. There's always a little bit of partial reflection. But this is total, it's internal because it's inside the glass and it's reflection. TIR, total internal reflection. My suggestion is you learn my answer. If you want to do a little diagram to go along with it, great. I mean, there is 3 marks for it. A fiber optic cable is made from a material which has a critical angle of 43.8. Calculate the refractive index. So, on your formula sheet, we have the sine of the critical angle. Sine C is 1 over n, where n is the refractive index, which is a property of the glass or whatever. Okay, so we want to work out n, so we'll rearrange the equation. So n is 1 over sine 43.8. That's the neighbour's dog having a good bark. Sine 43.8 equals, and on your calculator to 3 sig figs, that's 1.44, that is. And it doesn't have any units. Refractive index doesn't have units, it's a ratio. Figure 5 shows a point source of radio waves and 2 detectors that houses X and Y. So we have this thing here which is giving off radio waves, this transmitter here. Okay, and there's house X and there's house Y. And we look at the distances. That's 300 meters, that's 600 meters. Determine how the intensity at I compares with the intensity at X. Now, if you understand this, the equation, you should know that the intensity follows an inverse square law. So the intensity equals a constant divided by x squared. Now, we don't need to work out the constant. I mean, there's a hard way of doing this question. If I said that the intensity here was 100, and then what I could do is work out the value of K, and then when I know the value of K, I could work out the intensity at Y, and if I did that, I would get 25. But I know that an inverse square law means that if you double the distance, the intensity is a quarter. So how does the intensity at Y compare? It's a quarter. That's all I need to do. It's only 1 mark. Okay, so if you double the distance, the intensity is a half squared, which is a quarter. Okay. Compare the use of mobile phones, Bluetooth and Wi-Fi in communications. Your answer should include reference to their uses, frequencies and range. 6 marks. So this is our 6 mark question. And what is it asking us to do? So it wants us to give compare. So in other words, say what they have in common, say how they are different. Compare them. Compare what? Well, we've got 3 things here. We've got mobile phones, we've got Bluetooth, and we've got Wi-Fi. So we need to talk about mobile phones, Bluetooth, and Wi-Fi. What do we need to say? Well, your answer should include reference to their uses. So what are they used for? What frequencies do they use? And what is their range? And there are 6 marks. Now, I could write several pages on this, but there's only 6 marks. So we need to try and cover what it asks us to do. But as soon as we've said 6 good marks worth, and we know plenty of information about these, I'll show you my answer anyway. And I could write loads more, but I'm not going to. I think I've written enough for 6 marks. This is my answer. Well, first of all, this isn't my answer. This is how I'm going to do it. Compare uses, frequencies, range. What things do they have in common? How are they different? That's my little plan. Okay. And my answer is this. Now, I'll leave it there for you to read it. On my videos, I've said for each of them, there's a list of information that you should learn. If a question comes up about Bluetooth, you can give, half a dozen different good bits of information about Bluetooth, etc., etc. And so you should be able to come up with an answer something like this. Okay, I'm not going to go through it. Read it for yourself. Hopefully you'll agree that's 6 marks worth. Okay, last question. This is the hardest question, I think. They've given us this graph. We've never seen this graph before. We have to figure out what it's on about. Let's have a read. Now, it shows the solar radiation spectrum at the top of the atmosphere and at sea level. So what does that mean? Well, if there's the Earth and there's the atmosphere, and there's solar radiation, in other words, waves from the sun, electromagnetic waves from the sun. Now, some of these waves are absorbed and some of them get through. So this top one, radiation at the top of the atmosphere, that's the stuff, at the top of the atmosphere. Radiation at the Earth's surface, that's what gets through. And the difference between them is what's absorbed. Okay, the difference between the 2 graphs is what is absorbed, and basically it depends on the wavelength. Now, you might have learned your wavelengths. You could answer this question just talking about wavelengths, as in the numbers on the graph, and hopefully you get full marks for that. You should know that, I tell my students to learn visible. Visible light is from about there to there. It's from about 450 nanometers to about 600 nanometers. So that's visible. Okay. Wavelengths less than visible on this graph, that's ultraviolet. So that's ultraviolet there. Then bigger than violet. All of this lot here is infrared. That's all infrared. Okay. We don't actually get to microwaves on this graph. Microwaves are over here somewhere. Okay. All of this is infrared. Now, that's going to be very helpful. So basically, looking at ultraviolet, some of the ultraviolet is absorbed completely and none of it gets through. Some of the ultraviolet does get through. Okay, looking on the graph, these wavelengths of ultraviolet here get absorbed completely, and then these wavelengths here, if you know a bit about ultraviolet, you might know there's UVA, UVB, UVC, okay, and it's the shorter wavelengths don't get through. Visible, for the visible light, some of the visible light gets through. In fact, most of the visible light gets through, the Roy G. Biv. Looking at infrared, we will see that there are some wavelengths of infrared don't get through. They are completely absorbed. Around here, around 1300 nanometers and around 1800 nanometers, that is absorbed. It's actually absorbed by water in the Earth's atmosphere, by clouds, if you like. But then some infrared does get through. This infrared gets through, this infrared gets through. So depending on the wavelength of infrared, some gets through, some doesn't get through. Now, there's a lot of information I've given you there. I did say this is the hardest question on the paper. Okay, this would be my answer, yeah? UV less than 450 nanometers. Some is absorbed, some gets through. Visible from 450 to 700 nanometers, all wavelengths are partially absorbed. Most of it gets through. And then microwaves, okay, at these wavelengths, some wavelengths get through easily, but most is absorbed. Yes? So these wavelengths, this is why your satellites use microwaves, because one of the reasons they use microwaves is because microwaves pass through the Earth's atmosphere easily. Anyway, good luck with that question. It's a smelly one.